In this lesson, we're going to take a look at the other special nuclear material that is of concern when we're talking about nuclear weapons, and that's plutonium. More specifically, we're going to talk about plutonium-239, but the other isotopes of plutonium are somewhat important. Now, plutonium-239, actually all of the plutonium isotopes, do not exist in nature. Now, they were created through natural processes, stellar events like nova and supernova, but this happened a really long time ago on the scale of, hundreds of millions to billions of years. The radioactive half-life of all the plutonium isotopes in comparison are much, much shorter, which means while it was naturally created a long time ago, there's none of it left today. So now this means that we have to produce our plutonium through artificial means. So how do we go about doing that? Well, if you'll recall back to the discussion we had earlier in the course with the different types of nuclear material, fissile, which can sustain a fission chain reaction, fissionable, which we can make it fission, but it doesn't produce high enough energy neutrons to continue the fission chain reaction, and then fertile, which is where we take an isotope and we, for the most part, we introduce a neutron to it, and then it turns into something else that can be fissionable or fissile. So in this particular case, let's look at this simplified diagram here on the left side of the screen. The fertile material that we're starting with for plutonium production is going to be uranium-238. So now uranium-238, if we introduce it to a neutron, it can capture that neutron and turn into uranium-239. Now, uranium-239 can do one of two things. It can further capture a neutron and then fission, so we don't have it anymore, or it can decay by emitting an electron or a beta particle, and this is known as beta decay, and turn into neptunium-239. Neptunium-239 can also capture a neutron and do something, become something else or fission, or it can undergo radioactive decay and become plutonium-239. So that's how we go from 238 uranium to 239 plutonium. But that's not the end of the story. Now, we have to use neutrons in order to create our plutonium-239 from 238, which means we have our material someplace that has a lot of neutrons. And for the most part, this occurs in something like a nuclear reactor, which, because it's fissioning U-235 all the time, is producing a large amount of neutrons that we can use to make our plutonium. But the downside to this is while we leave our material in the reactor so we can make more and more plutonium-239, other things are going to start happening. And this is shown at the top of the diagram, where plutonium-239, it can grab a neutron and then fission. So we've lost it and it's now useless. Or it can grab a neutron and turn into plutonium-240. Now, plutonium-240, as we'll see here towards the end of the lesson, is really not useful to us. In fact, it's something we don't want. However, plutonium-240 can grab another neutron and turn into plutonium-241, which is good because it's a fissile isotope. The bad news is that 241 can grab a neutron and turn into 242, another isotope we really don't want. So let's take a look more specifically on how this happens. So we have here at the bottom of the screen, we have these two different plots with two sets of colored lines. Now, what this represents is cross-sections for two different isotopes, plutonium-239 and plutonium-241. Now, the blue line for the leftmost plot is the probability that plutonium-239 will fission if it grabs a neutron. The green line below it is that it will take that neutron and instead of fissioning, it'll turn into plutonium-240. Now what we can see is they're pretty close. They're separated by about a factor of 10 for the most part until we get into this really, we'll call it interesting region. This is also known as the resonance region, wherein the probabilities fluctuate very widely depending on the structure, the nuclear structure of plutonium-239. And then once we get up to the higher energies, we see that the probability that it will grab a neutron and turn into plutonium-240, it goes down by quite a bit, while the fission cross-section, or probability, stays pretty constant. And we see almost the exact same thing happens with plutonium-241. Now, these cross-sections, this comparison is a lot to do with why these isotopes are fissile instead of just fissionable or even fertile. Now, if we look over here on the right-hand side, we have two more sets of plots where the lines are pretty well separated by many orders of magnitude. And in this case, we're basically looking at something called a fertile isotope, which can preferentially capture a neutron and turn into something else. Now, these two isotopes in question are at the top, plutonium-240, and at the bottom, plutonium-242. Now, what this is telling us is the gray line, which is the probability of capturing a neutron and turning into something else, is very much higher than the red line, which is the probability of fission. And it's the same for both isotopes. Now, when we get over here towards the higher energies, about 1 to 2.5 MeV, we see that the probability of capture, turning into something else, goes way down, while we see a pretty large increase in the probability of fission. Now, the discussion on the Watt spectrum and what kind of energies are required for a fissile isotope, we know that they peak at about 1 MeV, right? That's the most probable energy. So this cross-section is showing us that, well, this is not a fissile isotope. It has to be above that in order for its fission probability to be better than its capture. And the same goes with 242. So if you just take a look at the cross-sections, you can get a really good idea on whether or not you're looking at something that's fissile or something that's fertile or generally not fissile. Now, uranium-238 looks very much like either of the two on the right, and uranium-235 looks very much like either of the two at the bottom. And this is how we can characterize making our plutonium. Now, there is a spreadsheet that should be available to you that has a bunch of math in it, but it produces a plot. And it produces a plot that looks very similar to this, which is production of different plutonium isotopes inside of a normally functioning nuclear reactor. Now, the percentage of uranium-235, or the concentration as it shows here, which has some weird units, I still don't know what they are, it basically shows that over time, we're going to lose our uranium-235. And this makes sense because this is what's keeping our fission chain reaction running. So over time, we're going to keep losing them as they fission. Now, these other lines are more interesting to us when talking about plutonium. So if we look at plutonium-239 creation or concentration as a function of time, we see that it starts off being very little, but very rapidly we see an increase until it kind of goes into a flat line. At the same time, however, or a little bit shifted towards the left towards the right, is the production of all the other plutonium isotopes which follow 239. And what we can see is that the longer we leave something in the reactor, the longer we leave our fuel in the reactor, the more 240, 241, and 242 that we're going to produce. Now, the reason I gave you the Excel worksheet that already has this sort of built into it is because you can change the times and you can get a better idea of what's happening that's a lot different than this particular plot. In reality, what happens is if you leave this stuff in the reactor too long, your plutonium-239, you're basically going to start losing it. And you're going to lose it at a pretty decent rate as you move forward. And the same goes with plutonium-241. What you'll end up seeing is in the long term, you're going to see buildup of plutonium-240 and plutonium-242. Now, if we look at this in terms of percentages of what type of plutonium do we have, you can see that there's kind of these two black lines, vertical black lines, where I make a delineation between something called weapons-grade plutonium, which is greater than 93% plutonium-239 and less than 7% of the rest of it. And then moving all the way over here to reactor grade, which is something that contains about 20% or more of the other isotopes. And the reason we make this delineation between something weapons grade and reactor grade has to do with what those other isotopes actually do as a function of time. And we'll talk about that here in a little bit. Okay, I know a lot of you are going to be extremely pleased to see math, and especially math that looks pretty complicated. But it really isn't that complicated. It just kind of looks that way. If you understand the rules, it actually follows a pretty logical pattern. So what you're seeing here is something called a decay chain or a production chain. It doesn't really matter. And this is from something called the Bateman equation. And you can take that particular equation and manipulate it, and you can find out as a function of time for multiple isotope creation, like we saw with plutonium, how much of each one of those parts are you going to have? Now, again, this is a lot more complicated than it looks in one respect, which is you have to do this for every neutron energy or interaction probability. And so it's not just doing this once for singular energy, which is what's been done in the worksheet to give you just an idea of what's going on, but you would have to do this for all possible neutron energies that are being produced in that reactor. And so, you could be doing this thousands of times just to get a, more accurate picture that you could very well get with something, just doing this once or twice. So we have two different equations, and this is basically the big N means the number of atoms of whatever it is, okay, for a given time. This N0 or N naught, this is how many we started with. This big sigma, this means summation. This just means we're going to calculate a bunch of terms and then add them all together. That's all that means. Then if we look over here with this little alpha term, which is contained within this expression, this n of t expression, this alpha term has this big pi looking thing, and that is a capital Greek letter pi. And instead of adding, it means multiply. So we're going to calculate right here a whole bunch of terms and then multiply them all together. So big sigma is adding, and big pi means multiplying. Again, it looks nasty, but it's not too bad, and it lends itself to writing a program to do this for you. Now, once we start solving these things, we can solve them for, well, we only have one component, right? So we're only looking at, in this case, going from uranium-238 to plutonium-239. We just have one thing that tells us how many of them we have as a function of time. If we have two of them, like we're looking now, not just plutonium-239, but plutonium-240 as well. So now we have two different terms, and you can see them. They both have that E exponential. Okay, apparently I messed up. This should be, the last one on the bottom should say N3, which would be plutonium-241. And we have three terms now because we have to account for every successive term. So the first one only accounts for plutonium-239. The second one counts plutonium-239 and 240, and then the third one says 239, 240, and 241. So by using this mathematical formula, we can actually calculate on a theoretical basis how much of something are we going to have. Well, it's not really theoretical because some of these decay constants or half-lives have been experimentally determined. But you get what I'm trying to say. Now, again, I'm not going to make you try to do this, but I did feel that I should put the equations up so you can see where the numbers and the lines on the plots for plutonium production, where they're actually coming from. So I said they're theoretical, kind of, but not really. Well, that has to do with the decay constants and production constants. And remember when we saw those cross sections, they had that busy bit in the middle where the probabilities fluctuated quite widely. Some of that is from theory and some of that is from experimental determination. So again, that's why it's not a purely theoretical model. However, we can take and look at our interaction probabilities in two different ways. So the first one is what we just call, this is the decay probability or decay constant, which is lambda. Now lambda is related to the half-life by this one formula. So if you know the half-life, you can calculate the decay constant and vice versa. And this is purely has to do with radioactive decay of a particular isotope. Now we have another lambda here, which is the production constant, and it actually has a little bit of a different input to it. In this case, to know how much of a thing we're producing at any one time, we have to know, well, what's the probability that that reaction is going to happen, which is our cross-section, which is little sigma here. And we have to know how many things that could cause that reaction are available. And so that's our neutron population or flux represented here by phi. So again, these are pretty important. The one on the left-hand side is the radioactive decay constant, and the one on the right-hand side is the production constant. Now, when we saw those equations, I'll flip back, we noticed that there are a whole bunch of lambdas in here, okay? And these lambdas depend on what the particular isotope is, but they also depend on what type of reaction we're talking about. So when we're looking at overall production of the different plutonium isotopes, we need to make sure that the lambda that we're using includes all of the reactions. Or if we're looking at the production of something like 240, we're really only concerned with, well, the production constant from 239 to 240. So it can get pretty complicated pretty quickly. So what we can see is for our overall decay constant, we're looking at the constant for, or probability of, spontaneous fission plus emitting an alpha particle and decaying, emitting a beta particle and decaying. Our production constant, which is transmutation constant here, that takes into account the probability that it's going to capture a neutron and turn into something else, or it's going to capture a neutron and fission, or it's going to capture a neutron and spit 2 more neutrons out. It can do a bunch of things. In order of probability, the capture and the fission are most likely, and then when we start getting to things like 1 neutron in and 2 neutrons out, the probability falls off really rapidly. So when we do simplified calculations, we kind of ignore those. And then, of course, we have to have our phi, or the number of neutrons present, in order to cause all of those reactions. And then finally, our total constant is it's just the sum of our production constant and our decay constant. So again, what does it all mean? Well, as I said before, it means that if you're trying to produce plutonium in a high neutron flux environment like a reactor, you're going to produce the plutonium-239 that you want, but at the same time, it's going to fission, so you're going to lose some of it that way, and then it's going to turn into some other isotopes, so you're going to lose it that way as well. So at the same time that you're producing it, you're losing it. Now, it's not shown in the notes, and it's not shown on the Excel spreadsheet, but you're not just making those plutonium isotopes as you leave your material inside of that neutron environment. You're going to start producing some other stuff that's much higher up on the periodic table. And this includes things like americium, curium, neptunium, californium, and then some even higher stuff. But the probability starts going down really rapidly as you start moving towards the right on the periodic table. And this, again, the Excel spreadsheet that you're being given, it only does the calculation for thermal neutrons and not all of that other energy regions that you see in the cross sections. So the takeaway that you're probably getting from this is this seems incredibly hard to do. And how would you even do this to get a real picture of accuracy? Well, we don't. We write computer codes and let the computer do all the work. That's pretty much it. Now, I said previously that some of the other isotopes of plutonium are not things that we want if we're building a nuclear weapon. Those isotopes are plutonium-240 and 242. So let's take a look at the half-lives. So here we have plutonium-239 with a half-life of about 24,000 years. So not too bad. The radioactive decay mode of plutonium-239 can be spontaneous fission. But with such a long half-life, it means that at any one time, it's not really spontaneously fissioning and producing neutrons. However, if we look at plutonium-240, it has a much shorter half-life, and it also decays by spontaneous fission, which means that for, per unit mass, it's going to be producing a lot of neutrons for a given amount of time. And we don't want neutrons being produced inside the material for our nuclear weapon because, remember, the nuclear weapon needs that fission chain reaction, and it's started by neutrons. But if we have something that's creating neutrons just randomly, then our nuclear weapon could start that chain reaction before we intend it to, before it's even capable of sustaining it. And what's going to happen is you're going to produce a lot of radiation, a lot of heat, and have a malfunctioning weapon, which then is useless. So plutonium-241, it doesn't actually spontaneously fission, but it's got a pretty short half-life. I think 241 decays by alpha emission. So this isn't an issue at all for us to have. But then we have plutonium-242, which has a long half-life, but it spontaneously fissions a lot. And so what we end up with is even more spontaneous fissions per unit mass than 240. So if we take these numbers and we put them all together, right, we don't want these extraneous neutrons to set off our nuclear weapon before we want it to. If it does, we don't have a functioning nuclear weapon anymore. We have something called a fizzle. Okay. If we look at putting it all together, we see that we get about 2.8 neutrons per spontaneous fission. In this particular case, for 240, we get 0.45 spontaneous fission. So we get about 1 neutron per microsecond per kilogram of material. And then we see here with plutonium-242, we get about 2 neutrons per microsecond per kilogram of material. So what does that mean? If we have 8 kilograms of our plutonium, but 40% of it is our isotopes plutonium-240 and 242, that means that we're getting almost 2 neutrons per microsecond being emitted. Assuming that it takes 100 microseconds to assemble our critical volume, that means that while we're putting our critical volume together, we have 200 chances for that fission chain reaction to start before we're ready for it to start, which means, again, we get a fizzle and our weapon doesn't function as intended. So producing plutonium, it's not super straightforward. There's a whole bunch of things that are going on in addition to making the thing that we want. And making these other things impact on how well it can be used as a nuclear weapon. That's not to say that you need weapons grade plutonium to create a nuclear weapon. In fact, there's an article in the reading material that talks about creating a nuclear weapon from reactor grade material, or something that contains more than 20% of these undesirable plutonium isotopes. So something to keep in mind. Now in the next lesson, we're going to talk about actually, once we've made the plutonium, how do we extract it from the material we made it from? In this case, uranium-238, 235 fuel mixture from a nuclear reactor.